somewhere past the orbit of Neptune. A spacecraft the size of a small piano just woke itself up after 321 days of sleep. It had been drifting through darkness so complete that its own instruments are right now its only company. When it confirmed it was still alive and still working, that signal needed nearly 9 hours to crawl across the gap at the speed of light before anyone on Earth heard it. The spacecraft is New Horizons, and it is currently coasting through a region most people assume is basically nothing. A gap. The blank space after the last planet on the poster. That assumption is wrong, and it has been wrong for a long time. Beyond Neptune lies a vast, frozen, and surprisingly busy frontier. Worlds with active glaciers. Mountains capped in frozen methane instead of snow. Structures that look like volcanoes, but erupt ice instead of lava. And a haze of dust so much thicker than predicted that it is forcing scientists to question where the outer solar system actually ends. This region has a name almost everyone has heard. The Kuiper Belt. But the picture most of us carry around in our heads of what that name means is decades out of date. To understand why that picture is broken, it helps to start with the version most of us learned in school. 4 rocky planets close to the Sun, a belt of asteroids, 4 gas and ice giants further out, and then Neptune, the last of the giants, and after that, nothing worth naming. Maybe a dotted line for Pluto's orbit. Maybe a small label reading Kuiper Belt in gray apologetic text. The unspoken message of that diagram is that the interesting part of the solar system stops at Neptune, and everything past it is leftover debris too small and too distant to matter. That is not a small oversimplification. It is a fundamentally incorrect picture, and correcting it has become one of the more interesting stories in modern planetary science. Beyond Neptune is not emptiness. It is a structured, populated, gravitationally sculpted region that stretches for billions of miles, containing thousands of confirmed worlds and, by most estimates, hundreds of thousands more that no telescope has ever managed to catch. Let's start with scale, because scale is the first thing that breaks intuition out here. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. Numbers like that don't mean much on their own, so it helps to translate distance into time, specifically the time it takes light to cross it. Sunlight reaches Earth in about 8 minutes. To reach Neptune, that same light needs more than 4 hours. Send a radio message from Earth to a spacecraft parked at Neptune's distance, and you would wait upward of 8 hours just for the reply to come back. Every command, every course correction, every "are you still there?" crosses a gap so wide that real-time control simply does not exist out there. The Sun does not disappear at that distance. It remains, by far, the brightest point of light in the sky, but its heat has all but vanished. Sunlight at Neptune is roughly 900 times weaker than what reaches Earth's surface. Local noon on Neptune looks something like a deep twilight back home, bright enough to see clearly by, but with none of the warmth that light usually implies. Cloud-top temperatures plunge to around -214 degrees Celsius, making Neptune one of the coldest environments anywhere in the solar system. And Neptune, remember, is just the starting line for what comes next. For most of the 20th century, this region beyond Neptune was a theoretical prediction rather than an observed place. The solar system formed out of an enormous rotating disk of gas and dust, and there was no obvious physical reason for that disk to have simply stopped producing material right at Neptune's orbit. In 1943, the Irish astronomer Kenneth Edgeworth argued that a reservoir of small icy leftovers should exist beyond the last giant planet. In 1951, the Dutch-American astronomer Gerard Kuiper made a similar case, proposing a belt of frozen material too thin to have clumped into a full planet, but too substantial to have simply disappeared. History eventually attached Kuiper's name to the region, even though Edgeworth arguably got there first. Knowing something should exist and actually finding it, though, are very different problems. For decades, The only confirmed object out past Neptune was Pluto, spotted in 1930 by Clyde Tombaugh and classified as the solar system's 9th planet for the next 76 years. It looked for a very long time like a lonely outpost. Astronomers searched for neighbors and kept coming up empty, not because the neighbors weren't there, but because the technology of the time simply could not see them. These objects are small, typically ranging from a few kilometers across to a few hundred. They are dark, reflecting only a sliver of the already weak sunlight that reaches them, and they crawl across the sky at a pace so slow that identifying their motion against the background stars requires comparing images taken hours or even days apart. The breakthrough finally came in 1992, when astronomers David Jewett and Jane Lulu, observing from the Mauna Kea Observatory in Hawaii, spotted a faint object roughly 160 kilometers across, orbiting at about 44 times Earth's distance from the Sun. It was not Plato. It was not a comet in the traditional sense. It was precisely the kind of ancient, icy body that Edgeworth and Kuiper had predicted decades earlier, quietly sitting where it had been for billions of years. That single detection cracked the door open. Within a few years, dozens of similar objects turned up, then hundreds, then thousands. As of 2025, more than 5,000 trans-Neptunian objects have been formally cataloged, and the models suggest that number is a rounding error compared to what's actually out there. Current estimates put the population at roughly 100,000 objects larger than 100 kilometers across, with potentially billions of smaller fragments down to the size of boulders and pebbles. And yet, despite that enormous number of bodies, the total mass of the entire Kuiper Belt is modest, likely just a small fraction of Earth's mass spread thin across an absolutely enormous volume of space. This is not a narrow ring like the rings of Saturn. It is a broad, thick, donut-shaped structure stretching from around 30 astronomical units near Neptune's orbit out to at least 50 astronomical units, and quite possibly much farther. That shape is not an accident. Neptune did not just happen to sit at the inner edge of a field of debris. Neptune built that field. Its gravity is the dominant sculptor of everything in this region. And understanding how that sculpting happened is the key to understanding why the belt looks the way it does today. Neptune, according to the leading models of early solar system evolution, did not form where it currently orbits. It formed closer to the Sun and slowly migrated outward over hundreds of millions of years. As it moved through the primordial disk of icy material, its gravity interacted with countless small bodies. Some were flung inward, eventually becoming the source of short-period comets. Some were hurled outward on the wild, elongated paths that carry them hundreds of astronomical units from the Sun before swinging back. And some were caught in gravitational resonances, stable orbital relationships where a small body completes a precise, repeating ratio of orbits relative to Neptune's own. The most famous of these is the 2-to-3 resonance, in which an object completes exactly 2 orbits around the Sun for every 3 that Neptune completes. Pluto sits in this resonance, along with thousands of other bodies collectively called Plutinos. Their orbits cross Neptune's path, which would ordinarily be a recipe for disaster, but the resonance acts like a scheduling agreement that keeps them from ever meeting Neptune at the wrong moment. Without that protective rhythm, Pluto likely would have been ejected from the solar system or smashed apart billions of years ago. Other resonances exist at different ratios, each one trapping its own population and giving the Kuiper Belt its underlying skeletal structure. Between these resonant populations sits what astronomers call the cold classical belt, a group of objects with low orbital tilts and nearly circular paths. These bodies appear to have formed more or less where they still orbit today, largely undisturbed by Neptune's long migration. Their surfaces tend to be unusually red, a color linked to ancient organic compounds slowly cooked by billions of years of cosmic ray exposure. This population is thought to be the most pristine sample of material left over from the solar system's construction. A genuine time capsule from 4.5 billion years ago. In sharp contrast is the scattered disk, a much more chaotic population with steeply tilted, highly stretched orbits that can carry objects from near Neptune's distance out to hundreds, or even thousands of astronomical units before looping back. These bodies were not gently placed on their current paths. They were essentially slingshotted there by close gravitational encounters with Neptune, and many of them remain unstable over long timescales, destined eventually to be ejected entirely or nudged inward to become centaurs. The transitional bodies that drift between the giant planets before sometimes becoming short-period comets. Eris, the most massive known dwarf planet, belongs to this scattered population. Its orbit carries it from about 38 astronomical units at closest approach out to nearly 98 astronomical units at its farthest, a single lap taking roughly 558 years. At its current distance of about 96 astronomical units, sunlight needs over 13 hours just to reach it. Eris is slightly more massive than Pluto, although Pluto is slightly larger by volume, a strange little discrepancy that ended up triggering a genuine crisis in planetary classification. When Eris was discovered in 2005, astronomers were forced to confront an uncomfortable question. If Pluto counted as a planet, then Eris had to as well, and so did every other comparable body waiting to be found out there. In 2006, the International Astronomical Union resolved the dilemma by creating an entirely new category, the dwarf planet, and moving Pluto into it. People still argue about that decision today, but the underlying science was never really in question. Pluto was never alone out there. It was simply the first member found of a much larger and more diverse family. That family now includes several confirmed dwarf planets, each one genuinely distinct. Pluto, with its nitrogen glaciers and 10 atmosphere. Eris, dense and remote, with a moon called Haumea. Haumea, an oddly egg-shaped body spinning so fast that it has stretched itself into an elongated form, complete with a family of collisional fragments and a ring system confirmed through stellar occultation observations in 2017. Makemake, a methane-rich world roughly 2/3 the size of Pluto, orbiting at about 45 astronomical units and completing one trip around the Sun in roughly 310 years. And Gong, a reddish scattered disk dwarf planet accompanied by a moon called Shangliu. Beyond these confirmed worlds sit dozens of additional trans-Neptunian bodies, large enough that they probably qualify for the same category but have not yet received formal classification. In the span of a single human generation, the outer solar system went from containing exactly one known body past Neptune to containing thousands. That explosion of discoveries revealed something the old textbook picture never anticipated. The Kuiper Belt has internal architecture, population boundaries, density gaps. Some features, like the resonant families and the split between the dynamically hot and cold populations, follow cleanly from well-tested models of Neptune's migration. But other features have proven far harder to explain, and one in particular has quietly become one of the most disruptive puzzles in modern planetary science. For years, observers noticed that the classical Kuiper Belt seemed to end abruptly. Object density dropped sharply near 50 astronomical units, and beyond that point, the known population thinned out dramatically. For a long time, this was treated as a genuine boundary, the point where the original planet-forming disk simply ran out of material, or where some dynamical process had swept the region clean. That interpretation was tidy, satisfying, and, as it turns out, increasingly hard to defend. The trouble started with dust. New Horizons carries an instrument called the Student Dust Counter, built to measure impacts from microscopic interplanetary particles along the spacecraft's entire flight path. Dust out here is mostly produced two ways: through collisions between Kuiper Belt objects and through the slow sandblasting effect of interstellar dust grains streaming in from beyond the solar system. Models predicted the dust density should peak somewhere around 40 astronomical units near the heart of the classical belt, and then fall away as the spacecraft passed the belt's presumed outer edge. That is not what the instrument recorded. As New Horizons crossed 40 astronomical units, the dust density did not decline. It stayed elevated through 45, 50, and 55 astronomical units. The dust kept arriving at rates 2 to 3 times higher than the models expected. A study published in the astrophysical journal Letters in early 2024 documented these unexpectedly high readings continuing all the way out to 55 astronomical units, with no sign of the drop-off anyone had predicted. A follow-up analysis in 2025 explored whether the excess could be explained by the behavior of the dust grains themselves, icy particles being pushed outward by solar radiation pressure, or losing their volatile coatings to ultraviolet light in a way that changes how strongly radiation pressure affects them. Both mechanisms likely play some role, but a third explanation loomed larger, and it was harder to wave away. The population of parent bodies producing all this dust may extend far past the region where ground-based telescopes have actually found Kuiper Belt objects. The dust, in other words, is a signal from somewhere we cannot yet see directly. Evidence that something out there is still generating debris in a region that was supposed to be nearly empty by now. Independent evidence arrived from a completely different direction. The New Horizons science team, working with the Subaru telescope's wide-field camera in Hawaii, ran deep surveys along the spacecraft's projected path. In 2024, they published results in the Planetary Science Journal reporting candidate trans-Neptunian objects at distances approaching 90 astronomical units, nearly double the classical belt's supposed edge. The sample was small, and the orbits of these candidates were not yet well determined, but the detections were consistent with a distant population that every previous survey had simply missed. New Horizons principal investigator, Alan Stern, described the findings as possible evidence for a second Kuiper Belt, an extended outer population beyond the one we've already mapped. That phrase needs careful handling. A second Kuiper Belt is not a confirmed discovery. It's a candidate interpretation built on limited data. The objects the Subaru survey detected could belong to the scattered disk, or they could be unusual outliers of the classical population on strange orbits. Sorting out which explanation is correct requires tracking these objects across multiple years to pin down their orbits precisely, and that work is still ongoing. But taken together, the elevated dust readings and the candidate distant detections point in a consistent direction. The outer solar system does not simply stop where the textbooks have been telling us it stops. The timing of this realization matters more than it might seem. For decades, that sharp edge near 50 astronomical units functioned as a boundary condition, a constraint that models of planet formation used to set the size of the original solar nebula. Theories of Neptune's migration were tuned to reproduce that edge. It was treated, essentially, as a settled fact of nature. That fact is now under active revision, and the consequences ripple through every model built on top of it. Because the Kuiper Belt is not just a collection of icy leftovers drifting in the dark. It's a fossil record. The sizes, orbits, and compositions of these objects encode information about the conditions that existed when the solar system was still forming, more than 4.5 billion years ago. If the belt turns out to be larger than assumed, if meaningful populations of objects exist beyond 50 astronomical units in a region we thought was cleared out, that changes our picture of the initial conditions. It suggests the solar nebula may have been more extensive than current models allow. that Neptune's gravitational influence shaped a larger volume of space than anyone calculated, and that the transition from the tidy, well-ordered planetary system into the chaotic frontier is not a clean line at all, but a gradual, poorly mapped fade. It helps to hold the scale of all this in your head for a moment. Imagine compressing the entire solar system down into a model where Earth orbits 1 meter from the Sun. On that scale, Neptune sits about 30 meters out, and the outer edge of the classical Kuiper Belt sits around 50 meters away, roughly the size of a generous backyard. But the scattered disk stretches far past that boundary. Sedna, one of the most distant known objects, swings from about 76 astronomical units at its closest, approach out to roughly 937 astronomical units at its farthest. On our 1-meter model, Sedna's farthest point would sit almost a full kilometer from the Sun, and the hypothesized Oort cloud, the vast spherical shell of icy bodies believed to be the source of long-period comets, may extend out to 50,000 or even 100,000 astronomical units. On the same model, that outer edge would sit somewhere between 50 and 100 kilometers away in every direction. The Kuiper Belt, in other words, is not the outer edge of the solar system. It is only the beginning of the outer solar system. Neptune's relationship to all of this is genuinely paradoxical. It is simultaneously the region's guardian and its slow, patient destroyer. Its resonances protect populations like the Plutinos, locking them into stable orbits that have held for billions of years. But its gravity also steadily erodes anything that isn't tucked safely into one of those protective rhythms. Any Kuiper Belt object that drifts too close to Neptune risks being flung inward toward the Sun, outward into the scattered disk, or ejected from the solar system entirely. Over billions of years, this process has thinned the belt's population considerably. What we observe today is a remnant, a fraction of the original material that survived Neptune's long gravitational sorting. That erosion has not stopped. It's still happening, continuously and quietly, right now, which is one of the reasons the sharp edge near 50 astronomical units was so puzzling in the first place. Neptune's gravitational reach weakens significantly with distance, and objects beyond about 50 astronomical units are largely outside its meaningful influence. If Neptune's gravity can't easily reach that far, then something else must be responsible for truncating the region, assuming the truncation is even real. Possible explanations include a natural limit to how far the original planet-forming disk extended, a passing star that stripped material away early in the solar system's history, or the gravitational influence of some undiscovered massive body lurking further out. None of these explanations has been confirmed, and each one carries implications that would ripple through the rest of planetary science if it turned out to be correct. What is confirmed, even setting aside any second belt or unseen extensions, is that the known Kuiper Belt is already a remarkably complex place. It hosts multiple dynamically distinct populations shaped by billions of years of gravitational back and forth with Neptune. It contains at least 5 recognized dwarf planets, probably dozens more waiting on formal classification, and objects ranging from tiny fragments to worlds well over 2,000 kilometers across. Their surfaces range from neutral gray to deep organic red, hinting at very different compositions and very different radiation histories. Some are rich in water ice. Some are coated in frozen methane and nitrogen. Some carry the dark reddish residue of organic compounds that have been slowly cooked by cosmic rays for longer than complex life has existed on Earth. These worlds are not identical, and they are certainly not simple frozen rocks drifting through nothingness. And yet, for all of that complexity, the single most unsettling fact about the Kuiper Belt might be how little of it we have actually seen. Current surveys can reliably detect objects roughly 100 to 200 kilometers across at distances of 40 to 50 astronomical units. Anything smaller, anything farther out, or anything sitting on an orbit that carries it away from the narrow band of sky most surveys concentrate on remains essentially invisible. The 5,000 or so catalogued trans-Neptunian objects represent the bright, nearby, relatively easy to find fraction of a population that almost certainly numbers in the hundreds of thousands at minimum. What we've mapped so far is a sketch, not a portrait. And every new telescope that looks a little deeper finds more objects, more structure, and more evidence that the outer solar system is richer than the previous generation of instruments could ever have revealed. That is about to change in a serious way. The Vera Rubin Observatory, which officially began its legacy survey of space and time in July of 2026, is expected to transform this picture almost completely. Equipped with the largest digital camera ever built for astronomical survey work, Rubin will scan the southern sky repeatedly over the course of a decade, imaging the same patches of sky with enough depth and enough frequency to catch the slow, faint signatures of distant trans-Neptunian objects that every prior survey has missed. Projections suggest the observatory could discover roughly 35,000 new Kuiper Belt objects within its first few years alone, multiplying the known population nearly tenfold. That flood of new data should finally reveal whether the outer edge of the belt is a genuine boundary or whether the population simply continues smoothly outward into regions no earlier instrument could reach. It will also test models of Neptune's migration with far greater statistical power, and it will search for the faint gravitational fingerprints of any massive unseen body hiding in the outer darkness. A question that has haunted planetary science for well over a decade. Rubin's full results, though, will take years to arrive. In the meantime, the only spacecraft actively exploring this region firsthand is New Horizons, currently drifting through the Kuiper Belt at roughly 64 astronomical units from the Sun. Its dust counter keeps recording impacts. Its plasma instruments keep sampling the solar wind. Its ultraviolet spectrograph keeps mapping hydrogen in the outer heliosphere. And the dust keeps arriving in quantities that no current model fully explains. From a region that was supposed to be effectively empty by now, nobody expected Pluto to have a heartbeat. Before New Horizons arrived in July of 2015, the best image humanity had of Pluto's surface was a handful of blurry pixels from the Hubble Space Telescope. Scientists could make out patches of light and dark material and infer, from spectroscopy, that nitrogen, methane, and carbon monoxide ices were present somewhere on the surface. They knew Pluto had a thin atmosphere and a large companion moon, but the geology, the texture, the actual landscape, all of it remained a mystery. Pluto had been little more than a smudge of light for 85 years, ever since Clyde Tombaugh first spotted it drifting slowly across photographic plates in 1930. The prevailing expectation going into the flyby was modest. Most scientists anticipated a geologically dead ice ball, cratered and inert. An interesting but ultimately simple fossil left over from the solar system's formation. New Horizons shattered that expectation within hours of closest approach. The first high-resolution images revealed something so unexpected that mission scientists initially doubted their own instruments. Sprawled across Pluto's equatorial region was an enormous, heart-shaped deposit of bright ice, informally named Tombaugh Regio after Pluto's discoverer. The left lobe of that heart turned out to be one of the most remarkable geological features ever found anywhere in the solar system. Sputnik. Planitia is a basin roughly 1,000 kilometers across, comparable in area to the state of Texas, filled to a depth of several kilometers with solid nitrogen ice. Its surface is almost perfectly smooth, with essentially no impact craters. And in planetary science, a crater-free surface means exactly one thing. The surface is young. On a world 4.5 billion years old, a landscape without craters has to have been erased and rebuilt over and over again by some active process. That process turned out to be convection. The nitrogen ice filling this basin is not sitting still. It is slowly churning. Modest but sufficient thermal energy rising from Pluto's interior mobilizes the nitrogen ice at temperatures around 35 to 40 degrees above absolute zero, driving a sluggish overturn in which warmer nitrogen rises from below, spreads out across the surface, cools, and sinks back down at the margins. That circulation carves the surface into polygonal cells, each roughly 20 to 40 kilometers across, with darker troughs marking where the ice descends. The entire surface of this basin appears to renew itself on a timescale of roughly 500,000 years, which in geological terms is astonishingly fast. Nitrogen ice at these temperatures behaves in ways that have no equivalent in ordinary human experience. It is a solid, but a geologically soft one, deforming and flowing under its own weight, much the way glacial ice flows on Earth, just far more slowly. This softness lets nitrogen act as a genuine geological agent, filling basins, moving through valleys, and transporting material across hundreds of kilometers. Along the eastern edge of Sputnik Planitia, New Horizons image nitrogen glaciers actively flowing into the basin from surrounding highlands, complete with dark flow lines threading down narrow valleys and spreading into fan-shaped deposits where the terrain levels out. These are not fossilized remnants of ancient activity. They are moving right now, driven by the same volatile cycle that powers the basin's slow convection. Climate models show nitrogen ice sublimating off the sun-facing portions of the basin, entering the thin atmosphere as gas, drifting across the surface, and recondensing somewhere colder, redistributing material across the entire planet on timescales that stretch into the millions of years. Pluto essentially runs a nitrogen cycle that plays the same structural role as Earth's water cycle, just at temperatures where water itself behaves like solid rock. That comparison becomes literal once you look at the mountains surrounding Sputnik Planitia. Pluto's peaks are built from water ice, and at these temperatures, water ice has roughly the mechanical strength of granite. It does not flow. It does not deform. It holds its shape the way stone does on Earth. Ranges informally named after mountaineers, Edmund Hillary and Tenzing Norgay, rise 1 to 3 kilometers above the surrounding terrain, built from blocks of rock-hard water ice that appear to have been fractured and pushed around by tectonic forces. Their peaks are capped in white, but not with water frost. The white comes from methane frost, an effect that looks eerily like snow-capped mountains back home, but arises from entirely different physics. On Earth, temperature falls with altitude, and water vapor condenses as it rises. On Pluto, the methane concentration in the atmosphere actually increases with altitude, and at sufficient height, the air becomes cold and methane rich enough for frost to condense directly onto exposed rock. East of the heart-shaped basin, the terrain grows even stranger. A region called Tartarus Dorsa is covered in formations unlike anything found anywhere else in the solar system, towering blades of methane ice, each one hundreds of meters tall, standing in dense, parallel rows that stretch across hundreds of kilometers. These features resemble a terrestrial phenomenon called penitentes, the spiky ice formations found at high altitude in the Andes, but scaled up to an almost absurd degree. On Earth, penitentes might reach a meter or two in height. On Pluto, the same basic process, differential sublimation carved by sunlight hitting an icy surface at steep angles, has had millions of years and an essentially uninterrupted supply of methane ice to work with, producing a landscape of knife-edged ridges, so vast and so geometrically regular that from orbit, it resembles a frozen forest viewed from above. Then there are the volcanoes. South of Sputnik Planitia, New Horizons photographed a cluster of enormous mounds with undulating, hummocky flanks unlike any terrain previously documented in the solar system. The largest of these features rise several kilometers above the surrounding landscape and span 1 to 200 kilometers across. Their shape, broad domes with summit depressions, strongly resembles volcanic structures. But these are not lava volcanoes. They're cryovolcanoes, built from the eruption of icy material welling up from Pluto's interior. A 2022 study in Nature Communications concluded that ongoing cryovolcanic resurfacing shaped this entire region, requiring multiple eruption sites and an enormous volume of erupted material to create the observed terrain. The near-total absence of impact craters on these features indicates the most recent activity occurred within the past 1 to 2 billion years, and possibly much more recently than that. Elsewhere on Pluto, trench-like fractures and a suspected caldera show spectral signatures of water ice mixed with ammonia compounds that radiation tends to destroy fairly quickly on Pluto's surface, meaning their presence implies genuinely recent eruptions, likely less than 1 billion years old. The implication is hard to overstate. Pluto has enough internal heat to drive volcanic activity on a world smaller than Earth's moon, orbiting nearly 40 times farther from the Sun than we do, in an environment cold enough that liquid nitrogen counts as an ordinary geological material. Somehow, over 4.5 billion years, its interior has retained enough warmth to keep mobilizing icy mixtures and pushing them to the surface. The exact source of that heat is not fully settled. Radioactive decay in Pluto's rocky core is the most likely primary contributor, but whether residual heat from formation or tidal interactions with its large moon also play a role remains an open question. A 2026 paper in Nature Communications, bluntly titled to describe Pluto as dazzling, dynamic, and very much not dead, summarized the state of the science plainly. Pluto exhibits active geology and a genuinely dynamic atmosphere, and its authors suggested it should be treated as a preview of what to expect from other large trans-Neptunian worlds, not as some kind of exception. Even Pluto's atmosphere, thin as it is, roughly 100,000th the surface pressure of Earth's, supports active weather. Haze layers extend over 200 kilometers above the surface, built from organic particles produced when ultraviolet light breaks apart methane and nitrogen molecules in the upper air. Those haze particles eventually settle back down, contributing to the reddish-brown tint visible across much of Pluto's terrain. Winds on the order of 1 meter per second carve faint dark streaks into the surface, and the entire atmosphere itself is impermanent, its pressure rising and falling dramatically across Pluto's 248-year orbit as its distance from the Sun shifts and nitrogen ice alternately sublimates and refreezes. Current models suggest the atmosphere is near its peak pressure right now and will undergo a sharp decline within the next decade or so as Pluto's northern hemisphere shifts from summer into winter. A world whose atmosphere periodically collapses and later rebuilds itself over centuries is not, by any reasonable definition, a dead world. Charon, Pluto's largest moon, added its own layer of surprises to the story. At roughly 1,200 kilometers across, about half of Pluto's own diameter, the two bodies orbit a shared center of gravity suspended in the space between them, locked in a mutual tidal embrace where the same face of Charon always points toward Pluto. Scientists expected Charon to be the simpler of the two worlds, smaller, colder, and with fewer resources to power any kind of geological activity. Instead, New Horizons revealed a moon that had been cracked open from the inside. Charon's most dramatic feature is a network of enormous canyons and troughs, stretching across its equatorial and southern regions. The largest of these runs for over 1,000 kilometers, a rift valley deeper than the Grand Canyon slicing across a body barely a third the diameter of our own moon. A second canyon system in the southern hemisphere appears to reach depths of roughly 9 kilometers based on shadow measurements, making it one of the deepest known canyons anywhere in the solar system relative to the size of the body it crosses. These are not impact features. They're tectonic fractures, cracks formed when Charon's crust was pulled apart by forces originating deep within it. The leading explanation involves ice expansion. If Charon once held a subsurface ocean of liquid water that later froze solid, the roughly 9% volume increase that occurs when water turns to ice would have placed enormous stress on the overlying crust, cracking it in exactly the pattern visible in the canyon systems today. Those canyons are essentially the scars of a moon that froze from the inside out, its own solidifying ocean splitting its surface open. Whether any liquid remains at depth today is unknown, and the evidence doesn't require a present-day ocean, only a past one, though the timing remains genuinely ambiguous. Charon's North Pole tells a very different story. It's covered by a dark, reddish cap informally nicknamed for its resemblance to a dark fortress from fiction, visually striking against the moon's otherwise gray terrain. This cap is thought to be composed of complex organic molecules called tholins, built from simpler precursor compounds like methane and nitrogen. The leading hypothesis is that methane gas escaping from Pluto's atmosphere drifts across the gap between the two worlds, with some of it settling onto Charon's cold polar regions, where ultraviolet light and energetic particles from the solar wind slowly process it into heavier organic molecules that accumulate on the surface over millions of years. Charon isn't generating these compounds internally. It's catching them, drifting over from its partner world. A slow chemical exchange between two tidally locked bodies separated by roughly 19,000 kilometers of empty space. If Pluto demonstrated that large trans-Neptunian objects can be geologically complex, a much smaller world called Arrokoth demonstrated that even tiny ones can be scientifically profound. New Horizons flew past Arrokoth, once designated by a string of letters and numbers before receiving its permanent name. On the 1st of January, 2019, at a distance of roughly 3,500 kilometers, Arrokoth is a cold classical Kuiper Belt object, one of the primordial residents of the belt that appears to have formed close to where it still orbits and remained essentially undisturbed for billions of years. It's about 36 kilometers long, weighs almost nothing by planetary standards, and its shape turned out to be one of the most scientifically informative in the entire solar system. Arrokoth is a contact binary, made of two flattened lobes joined at a narrow neck, resembling a snowman that's been gently pressed together from both ends. The larger lobe is roughly twice the volume of the smaller one, and both are remarkably smooth, with very few impact craters, meaning this surface has accumulated almost no hits across 4.5 billion years of exposure. That emptiness carries deep implications for the Kuiper Belt's collision history, but what it reveals first is something about formation itself. This is not a body that was battered into its current shape through violent collisions. It's a body that was assembled gently and left alone. Detailed analysis of the lobe's alignment, the orientation of the spin axis, and the smoothness of the surface all indicate the two lobes formed near each other within a localized cloud of material that collapsed gently under its own gravity, became a gravitationally bound pair, gradually lost orbital energy, and eventually drifted together in an extraordinarily soft merger at speeds of only a few meters per second. The impact was gentle enough that neither lobe was significantly deformed. A 2026 study using numerical simulations confirmed that contact binaries like Arrokoth can form directly through the gravitational collapse of clouds of pebble-sized material in the early solar nebula, a process called streaming instability. That's a meaningfully different picture from the older model of small body formation, which imagined objects gradually building up through repeated high-speed collisions. Arrokoth's shape stands as evidence that at least some of these building blocks formed gently, assembling from small particles that clumped together under their own gravity in a calm, quiet environment. Its surface composition adds further support. Instruments aboard New Horizons detected clear signatures of methanol on Arrokoth's surface, but no definitive evidence of water ice. and the uniformly reddish coloring is consistent with organic compounds, slowly processed by billions of years of cosmic ray exposure. None of this looks like material that formed under violent conditions. It looks like the chemical fingerprint of patient, undisturbed processing in cold, quiet space. Arrokoth is less a planetary body and more a time capsule, a fragment of the original solar nebula preserved in the deep freeze of the outer solar system for longer than complex life has existed on Earth. But the revelations from the trans-Neptunian region haven't come only from spacecraft flybys. The James Webb Space Telescope, operating from its position near the Sun, Earth's second Lagrange point roughly 1.5 million kilometers from Earth, has turned its infrared instruments toward the outer solar system and uncovered chemistry that was completely invisible to every previous observatory. Makemake, the second largest classical Kuiper Belt object after Pluto, had long been considered one of the more enigmatic dwarf planets. It orbits at roughly 45 astronomical units and takes about 310 years to circle the Sun. Its surface was known to be covered in methane and ethane ices, but the finer details of its composition and any atmospheric activity remained uncertain. In 2025, a team using the James Webb Space Telescope reported the detection of methane gas around Makemake, making it only the second trans-Neptunian object after Pluto where atmospheric gas has been directly confirmed. The methane was identified through a process called solar excited fluorescence, in which sunlight is absorbed and then re-emitted by methane molecules floating above the surface. The detection suggests Makemake possesses either an extremely thin atmosphere in equilibrium with its surface ices, or an exosphere, a region where individual gas molecules escape the surface and follow ballistic arcs before falling back down or drifting off into space. Entirely. An even more striking discovery followed. In 2024, a research team led by Zaba Kiss reported a prominent excess of mid-infrared light coming from Makemake that could not be explained by simple passive thermal emission from a uniformly cold surface. The excess pointed to localized warm spots, small patches significantly hotter than the surrounding terrain. One interpretation is ongoing cryovolcanic activity, conceptually similar to the geysers on Saturn's moon Enceladus, though likely driven by a different mechanism. If confirmed, it would mean Makemake, a world roughly 2/3 the size of Pluto, orbiting in temperatures around 40 degrees above absolute zero, is actively venting material from its interior right now. The finding isn't yet definitive. The warm spots could have other explanations, including unusual surface thermal properties or patchy composition. But the data is consistent with a genuinely active world, and follow-up observations are already underway. Eris, the most massive known dwarf planet, delivered its own chemical surprise. Despite orbiting so far from the Sun that sunlight takes more than 13 hours to reach it, Eris and its moon Haumea became targets of James Webb observations measuring the deuterium to hydrogen ratio in the surface methane. That ratio functions as a kind of chemical fingerprint. Methane accreted directly from the primordial solar nebula carries a different ratio than methane produced by geological processes inside a body's interior, which in turn differs from methane delivered by cometary impacts. Measurements published in 2024 by Christopher Glean and colleagues found moderate ratios on both Eris and Makemake, inconsistent with a purely primordial origin. The results suggest hydrothermal or metamorphic processes deep inside these worlds have chemically reworked the methane, generating new methane through reactions between liquid water and rock at elevated temperatures far below the visible surface. In other words, at least some of the methane sitting on these frigid, distant worlds was not simply ancient frost inherited from the birth of the solar system. Some of it was manufactured internally through chemistry that requires liquid water interacting with minerals at depth. If that interpretation holds up, it implies Eris and Makemake have, or once had, warm interiors. warm enough for liquid water to persist at depth, warm enough for water rock chemistry to actually operate, warm enough to drive geological processes capable of replenishing surface volatiles from below. On worlds this small, this cold, and this far from the sun, that's a remarkable claim. But the chemical evidence supports it, and no alternative explanation has cleanly replaced it. The picture keeps widening. James Webb observations of Sedna, Gong, and Quaoar, published in 2024, revealed volatile ices and organic material on all three, with compositions suggesting that surface volatiles are being actively replenished rather than simply sitting unchanged since formation. Quaoar, a trans-Neptunian object roughly 1,100 kilometers across, turns out to possess a ring system, discovered through stellar occultation observations in 2023, a dense ring orbiting well outside the Roche limit, the distance within which tidal forces are supposed to tear a ring apart before it can survive. That ring's continued existence challenges standard models of ring dynamics and raises the question of whether it's being actively replenished by material shed from Quaoar's own surface. Haumea, the rapidly spinning, elongated dwarf planet whose shape resulted from an ancient collision that shattered a larger parent body and scattered a family of fragments, also hosts a ring system detected through stellar occultation back in 2017. Haumea spins so quickly, completing a full rotation in under 4 hours, that it's been stretched into a shape resembling a flattened rugby ball. Its surface is dominated by crystalline water ice, which is genuinely unusual since cosmic radiation should have converted that ice into an amorphous, disordered form over billions of years of exposure. The presence of crystalline ice suggests either recent resurfacing or some ongoing energy input that keeps recrystallizing the surface. Haumea's 2 moons continue to be studied for clues about the orbital history of the entire system. Taken together, a dwarf planet, a ring, a family of collisional fragments, and 2 moons represents a level of dynamical complexity that would have seemed implausible for a body this far from the sun before it was actually observed in detail. What makes all of this even more remarkable is that the scientific community received an early warning decades before New Horizons ever reached Pluto. In 1989, Voyager 2 flew past Neptune and turned its cameras toward Triton, Neptune's largest moon. Triton orbits Neptune backward, opposite to the planet's own rotation, which is powerful evidence that it didn't form alongside Neptune at all, but was instead captured from an independent orbit around the Sun. Most planetary scientists now consider Triton a captured Kuiper Belt object, a trans-Neptunian world that wandered too close to Neptune and got pulled permanently into orbit around it. If that's correct, Triton is the only large trans-Neptunian body besides Pluto that a spacecraft has ever studied up close. What Voyager 2 found was extraordinary for its time. Triton's surface looked geologically young, with very few impact craters. Its southern hemisphere was blanketed in a pinkish frost of nitrogen and methane ice. And most remarkably, the spacecraft observed active geysers in real time. Dark plumes of nitrogen gas and entrained dust erupting from the surface to heights of roughly 8 kilometers before being swept sideways by thin upper atmosphere winds into long horizontal streaks. These were live eruptions captured by a passing spacecraft on a world where surface temperatures measured around negative 235 degrees Celsius. Triton demonstrated, back in 1989, that geological activity could persist on an icy body far from the sun, at temperatures cold enough to freeze nitrogen into a solid. In many ways, that observation should have prepared the scientific community for what New Horizons would eventually find at Pluto 26 years later. It did, to a degree, but the sheer breadth of active processes on Pluto, convection, glacial flow, cryovolcanism, atmospheric cycling, the enormous bladed terrain, still managed to exceed even the expectations Triton had set. Triton remains an enticing, largely unfinished target. No spacecraft has returned there since that 1989 flyby, and the hemisphere that wasn't photographed during the brief encounter remains entirely unmapped. Its interior structure, the possibility of a subsurface ocean, and the exact mechanism behind its geysers all remain unresolved. If Triton really is a captured Kuiper Belt object, studying it closely would offer a window into what a large trans-Neptunian world looks like after billions of years of tidal heating and gravitational interaction with a giant planet. A very different evolutionary path from the cold isolation that Pluto and the other dwarf planets have experienced. Every new observation reinforces the same conclusion. The trans-Neptunian region is not a freezer full of inert leftovers. It's a gallery of active worlds, complex interiors, and chemical processes still running billions of years after formation. Pluto has glaciers and cryovolcanoes and an atmosphere that rises and collapses with its orbit. Charon carries the fractured scars of a frozen internal ocean and wears a cap of organic material, delivered from its partner world. Arrokoth preserves the gentlest moments of planetary formation in its undamaged snowman-shaped body. Makemake vents methane gas and may host active warm spots. Eris and Makemake appear to manufacture methane through interior chemistry that requires liquid water. Quaoar and Haumea wear rings that defy straightforward explanation. Sedna and Gongong show volatile inventories that look replenished rather than static. And Triton, very likely a captured member of this same population, showed active geysers erupting from its frozen surface nearly 4 decades ago. The old assumption that distance from the sun equals geological death has been thoroughly overturned. These worlds sit at temperatures with no real terrestrial comparison. Cold enough that nitrogen behaves as a solid, methane behaves as rock, and water ice has the structural strength of granite. And yet they move, they flow, they erupt. They cycle gases through atmospheres thinner than a laboratory vacuum. They generate organic compounds and carry chemical signatures pointing toward warm, wet interiors hidden beneath crusts of ice harder than stone. The question is no longer whether these frozen worlds are geologically active. That evidence is overwhelming and keeps accumulating with every new telescope observation and every fresh analysis of existing spacecraft data. The real question now is how. How does a world the size of Pluto, receiving roughly 1/900th the sunlight Earth enjoys, hold on to enough internal energy to drive cryovolcanism for billions of years? How does a body the size of Makemake sustain methane gas above its surface and possibly vent warm material into space? How do objects this small avoid cooling into total inertness over the age of the solar system? Part of the answer lies in radioactive decay, the slow breakdown of uranium, thorium, and potassium isotopes locked inside the rocky cores of these worlds since their formation. That heat source is modest, but relentless, and inside a body insulated by kilometers of ice. It may be enough to keep interior temperatures above the melting point of certain ice mixtures for billions of years. Ammonia mixed with water ice, for instance, can stay liquid at temperatures far below the freezing point of pure water. And if these dwarf planets incorporated enough ammonia during formation, pockets of liquid could persist deep inside them even now. But radioactive decay alone probably doesn't explain everything. Tidal heating, the frictional warmth generated by gravitational flexing in bodies with eccentric orbits or large moons, may contribute in some systems. Residual heat left over from formation, the gravitational energy released as these bodies originally accreted, may have lingered longer than simple cooling models predict, especially if their insulating ice shells are thicker or more effective than assumed. And the chemistry itself might play a role, since certain reactions between water and specific minerals release heat, potentially sustaining warm localized pockets long after other heat sources have faded. None of these mechanisms has been fully pinned down for any individual trans-Neptunian object. The internal structures of Pluto, Eris, Makemake, and their neighbors remain largely unknown. No spacecraft has ever orbited any of them. No seismometer has ever listened to their interiors. No gravity mapping experiment has measured how mass is distributed inside their ice shells. What we have is surface observation, spectroscopic data, and thermal models constrained by known physics but limited by genuine ignorance. The interiors of these worlds rank among the least explored places in the entire solar system. And the surprises already found on their surfaces suggest what lies beneath could be stranger still. If these worlds are this complex, this active, this chemically dynamic, then the environment they inhabit demands a second look. These are not passive objects drifting through empty space. They behave like geological systems powered by internal energy sources, shaped by processes scientists are only beginning to catalog. This environment was supposed to suppress all of that. It was supposed to be too cold, too dark, too far from any energy source for anything interesting to happen. And yet it's happening, seemingly everywhere astronomers look with enough resolution. The frozen worlds of the outer solar system keep refusing to be simple. There is a moment during every outbound journey from the sun when the rules of the environment quietly change. It doesn't happen at a marked boundary. There's no line in space where warmth becomes cold or light becomes dark. The change is gradual, governed by one of the simplest and most unforgiving relationships in physics, the inverse square law. Light intensity falls off with the square of the distance from its source. Double your distance from the sun, and the light reaching you drops to a quarter of what it was. Triple the distance, and it drops to a ninth. Move 10 times farther out, and it falls to 100. The arithmetic is simple. The consequences are severe. At Earth's distance from the sun, solar radiation delivers roughly 1,360 watts of energy per square meter. More than enough to power photosynthesis, warm oceans, drive global weather, and sustain every living thing on the planet. At Jupiter, 5 times farther out, that figure drops to about 50 watts per square meter. At Saturn, nearly 10 times Earth's distance, it falls to roughly 15 watts. At Neptune, 30 times farther from the Sun than Earth, the number collapses to approximately 1.5 watts per square meter, less than 1/100% of what Earth receives. The warm, energy-rich environment that makes life possible on our planet has been stripped away, almost entirely by the time you reach the last giant planet. And Neptune, again, is only the threshold. Step past it into the Kuiper Belt, and the numbers keep getting more extreme with every additional astronomical unit. At 40 astronomical units, roughly Pluto's average distance, solar intensity drops to around 0.08 of a watt per square meter. Sunlight now about 1,600 times weaker than on Earth. To put that in more human terms, if you stood on Pluto's surface at local noon and looked toward the sun, you'd see a brilliant point of light, still by a wide margin the brightest thing in the sky, still bright enough to cast a faint shadow and clearly recognizable as the sun, but with essentially none of its warmth remaining. The illumination would sit somewhere between a deep Earth twilight and a bright, moonlit night, bright enough to read by, but incapable of warming your skin at all. At 50 astronomical units, where the classical Kuiper Belt was long assumed to end, sunlight weakens further, to roughly 0.05 of a watt per square meter, about 2,500 times fainter than on Earth. At 64 astronomical units, where New Horizons currently drifts, the intensity falls to around 0.03 of a watt per square meter. Picture a single candle burning at the far end of a football stadium. You can see the light. It reaches your eyes, but it does nothing useful to illuminate anything around you. The temperature consequences follow directly from that physics. Without meaningful solar heating, surface temperatures on trans-Neptunian objects are set almost entirely by a feeble balance between the trace sunlight they absorb, the thermal radiation they lose back into space, and whatever small amount of internal heat a given body happens to generate. Most Kuiper Belt objects sit somewhere between 30 and 50 degrees above absolute zero, roughly -220 to -240 degrees Celsius. At those temperatures, nitrogen behaves as a solid that can flow like glacial ice under pressure. Methane behaves as a rigid crystalline material. Carbon monoxide freezes into a hard frost. And water ice takes on the mechanical properties of bedrock. The chemistry unfolding on these surfaces operates in a regime so cold that substances we normally think of as gases and liquids behave instead like minerals and stone. These conditions don't just make the outer solar system inhospitable. They make it operationally hostile to nearly every tool humanity has ever built for exploring space. Consider the basic problem of power. Every spacecraft needs electricity to run its instruments, process data, keep sensitive components from freezing solid, and transmit signals back to Earth. In the inner solar system, solar panels handle that job reliably. Mars rovers, spacecraft orbiting Venus and Mercury, probes studying the Sun itself, all of them harvest sunlight and convert it directly into usable power. Even at Jupiter, solar power remains marginally viable. The Juno mission orbiting Jupiter carries the largest solar arrays ever deployed on an interplanetary spacecraft, each wing stretching nearly 9 meters, generating just enough power to keep the mission running at 5 astronomical units from the Sun. Beyond Jupiter, though, solar power effectively dies. The sunlight is simply too weak, and the panels required to gather a usable amount would be implausibly enormous. Every spacecraft that has ever ventured deep into the outer solar system, the 2 Pioneer probes, both Voyagers, New Horizons, and Cassini at Saturn, has relied instead on radioisotope thermoelectric generators, devices that convert heat released by the natural radioactive decay of plutonium-238 directly into electricity. These generators are reliable, extremely long-lived, and completely independent of sunlight, but they're also heavy, expensive to fuel, and limited in how much power they can actually produce. New Horizons launched with a single generator producing roughly 240 watts of electrical power, less than the output of 3 ordinary household light bulbs. By 2026, radioactive decay had reduced that output to around 190 watts. The spacecraft has to run every instrument, heat every sensitive component, and transmit data across nearly 10 billion kilometers of space, on a power budget that would struggle to run an ordinary desktop computer. That power constraint shapes essentially everything about how the outer solar system gets explored. Instruments have to be engineered for extreme efficiency. Data has to be compressed and transmitted slowly in small pieces. Heaters have to be rationed carefully. Some instruments have to be switched off entirely while others run, because operating everything simultaneously would exceed the available power. The New Horizons team has developed updated autonomy software specifically to manage operations at ever greater distances from the Sun. Where power keeps declining and communication delays keep growing, that communication brings its own set of challenges. Radio signals travel at the speed of light, and from 64 astronomical units, a one-way signal needs roughly 8 hours and 52 minutes to reach Earth, a full round trip. Command sent and response received takes nearly 18 hours. Real-time control simply isn't possible at that distance. Every action the spacecraft takes has to be planned, programmed, and uploaded days or even weeks ahead of time. If something goes wrong, the spacecraft has to detect the problem and respond entirely on its own, long before ground controllers back on Earth even know there's an issue. When New Horizons flew past Pluto back in 2015 at roughly 33 astronomical units, the communication delay was about 4.5 hours each way. At its current distance, that delay has nearly doubled, and it will keep growing for as long as the spacecraft continues to operate. Signal strength compounds the difficulty further. since radio power fades with the square of distance, exactly like sunlight. At 64 astronomical units, the signal reaching Earth from New Horizons is extraordinarily faint, measured in fractions of a billionth of a watt. Capturing it requires the largest radio dishes on the planet, the 70-meter antennas of NASA's Deep Space Network, pointed with precision at the spacecraft's position for hours at a stretch. Data rates end up correspondingly slow. Information a home internet connection could download in a fraction of a second can take hours to transmit. From the outer Kuiper Belt, the complete data set from the Pluto flyby took over a year to fully download after the encounter itself was already finished. These engineering constraints mean the outer solar system isn't explored through sweeping surveys. It's explored in narrow, painstakingly targeted glimpses. Right now, there is exactly one spacecraft operating inside the Kuiper Belt. Exactly 2 trans-Neptunian objects have ever been photographed up close by a passing camera: Pluto and Arrokoth. Everything else we know about the thousands of remaining objects in this region comes from telescopes on or near Earth, straining across billions of kilometers of empty space at targets that are small, dark, and moving with agonizing slowness. And this is exactly where the detection problem becomes acute. Finding trans-Neptunian objects from Earth ranks among the hardest observational challenges in astronomy. These bodies are faint almost beyond intuition. A typical Kuiper Belt object, a few hundred kilometers across, orbiting at 45 astronomical units and reflecting only a small fraction of the already weak sunlight reaching it, appears at a visual magnitude of around 23 to 25. For comparison, the faintest star visible to the unaided human eye sits around magnitude 6. Every 5 magnitudes of difference represents roughly a 100-fold change in brightness, which means an object at magnitude 25 is something like 40 million times fainter than the dimmest star you could possibly spot with your naked eye on the clearest, darkest night imaginable. Detecting something that faint requires a large telescope, a highly sensitive digital camera, and exposure times measured in minutes per image. Faintness, though, is only half the problem. The other half is motion, or rather the near total absence of it. Trans-Neptunian objects orbit the Sun at such vast distances that their apparent motion across the sky, as seen from Earth, is minuscule, typically just 1 to 3 arcseconds an hour, so slow that in a single image, such an object is completely indistinguishable from a background star. Finding one requires taking multiple images of the same patch of sky, hours apart, and carefully comparing them to spot any faint point of light that has shifted position ever so slightly. This technique, often called shift and stack, relies on sophisticated software that tests thousands of possible motion rates and directions, digitally shifting and combining image frames to see whether a faint source pops out at any particular combination. The computational load is enormous. A single field of view from a large survey telescope might contain hundreds of thousands of stars and galaxies, and hiding somewhere among them might be 1 or perhaps 2 genuine Kuiper Belt objects. Separating that faint signal from the noise, cosmic ray hits, detector artifacts, and every other source of false positives that plagues deep astronomical imaging requires serious processing power and carefully engineered algorithms. The search for Arrokoth illustrates just how excruciating this process can get. After New Horizons flew past Pluto in 2015, the mission team needed a second target reachable with the spacecraft's remaining fuel. But no known object happened to sit within the narrow cone of space New Horizons could actually steer toward. The team had to find one from scratch. They enlisted the Hubble Space Telescope for a dedicated search, pointing its cameras at fields along the spacecraft's projected flight path and hunting for the faint, slow-moving signature of an unknown object sitting at the right distance, on the right trajectory, within the spacecraft's limited steering range. The search consumed dozens of Hubble orbits, some of the most competitively allocated telescope time on Earth, and sifted through thousands of background sources to identify viable candidates. In the end, the team found only one object close enough to the flight path and bright enough for New Horizons. Cameras to observe during approach. Arrokoth. The margins were razor thin. Had it been a few hundred kilometers farther from the flight path, or slightly fainter, or on a slightly different orbit, that flyby simply would not have happened. The most detailed observations ever made of a primordial Kuiper Belt object depended on finding a needle in a haystack, stretching across the outer solar system. And the needle was found with less than 3 years to spare. This is part of why the known population of trans-Neptunian objects has grown so slowly. Despite decades of dedicated surveying, only about 5,000 have been formally cataloged, and each one represents a genuine investment of telescope time, computational effort, and follow-up observation needed to confirm the detection and pin down its orbit. The objects found so far are overwhelmingly the brightest, nearest members of the population, the tip of an iceberg whose full extent remains unknown, and the difficulty only increases with distance. An object at 80 astronomical units, reflecting the same fraction of sunlight as an equivalent body at 45 astronomical units, would appear roughly 10 times fainter, simply because it receives less sunlight to begin with and sits farther from our telescopes. That double penalty, less illumination and greater distance, means the detection horizon for Kuiper Belt objects drops off steeply as distance increases. Current surveys can reliably spot objects a few hundred kilometers across out to roughly 40 or 50 astronomical units. At 80 or 90 astronomical units, only the very largest objects, those exceeding roughly 1,000 kilometers in diameter, would be bright enough to register at all. Everything smaller is effectively invisible. This observational bias matters enormously for interpreting that apparent outer edge near 50 astronomical units. The sharp decline in known objects there might be genuine, reflecting a real drop-off in population. Or it might simply be an artifact of detection limits, objects that are actually present but too faint and too distant for existing surveys to catch. Telling these two possibilities apart requires either much deeper surveys, which is exactly what the Vera Rubin Observatory's legacy survey of space and time is designed to provide, or indirect measurements that don't depend on reflected sunlight at all. The dust readings from New Horizons are precisely that kind of indirect evidence, and their significance becomes clearer once you understand the underlying physics of how dust actually gets produced and distributed throughout the Kuiper Belt. Dust in the outer solar system doesn't primarily arrive from interstellar space, though a small background component genuinely does. The dominant source is the Kuiper Belt itself. Collisions between Kuiper Belt objects, even gentle, glancing ones, grind material off their surfaces and release microscopic particles into the surrounding space. On top of that, the steady bombardment of these surfaces by high-speed interstellar dust grains acts something like a sandblaster, chipping away tiny fragments that join the local dust population. Over billions of years, these two processes have produced a diffuse cloud of dust pervading the belt, with particle sizes ranging from submicroscopic grains up to fragments a millimeter or more across. Once produced, dust particles don't simply stay put where they formed. They're subject to forces the larger parent bodies can more or less ignore. Solar radiation pressure pushes small grains outward, away from the sun, and the smaller the grain, the stronger the push relative to the sun's gravity, meaning the farthest drifting grains travel before other forces finally bring their orbits to a halt. Meanwhile, a subtler relativistic drag effect called the Poynting-Robertson effect slowly spirals grains inward over very long timescales. The balance between these competing forces, combined with gravitational nudges from Neptune and the other giant planets, determines where dust ultimately ends up and how it's distributed across the outer solar system. Models of this process, calibrated against the earliest student dust counter measurements as New Horizons crossed the inner Kuiper Belt, predicted a fairly straightforward profile. Dust density peaking somewhere around 40 to 42 astronomical units, where the concentration of parent bodies and the resulting collision rate is highest, then falling off beyond the belt's presumed outer edge near 50 astronomical units as the source population thins out. Radiation pressure would push some grains farther, but the overall density was expected to decline sharply. Tracking the drop in parent bodies, the dust counter simply didn't cooperate with that prediction. As documented in the Astrophysical Journal letters, in early 2024 and refined through further analysis in 2025, the instrument recorded impact rates between 40 and 50. 5 astronomical units that exceeded model predictions by a factor of 2 to 3. The expected decline near 50 astronomical units never materialized. Dust kept striking the detector at elevated rates as the spacecraft pushed deeper into and beyond the outer belt. 3 hypotheses have emerged to explain this discrepancy, and each one carries genuinely different implications for the structure of the outer solar system. The first focuses on the dust grains themselves. Kuiper Belt dust isn't pure rock. Many grains likely contain volatile ices, water ice, carbon dioxide ice, possibly more exotic frozen compounds. When icy grains are exposed to solar ultraviolet radiation, a process called photosputtering erodes their volatile component, shrinking their mass and size. A smaller, lighter grain responds more strongly to radiation pressure and gets pushed farther from the sun before other forces bring it to a stop or destroy it entirely. If photosputtering turns out to be more efficient than existing models assume, the dust distribution would stretch farther outward, maintaining elevated densities well past where the actual parent bodies are found. This explanation leaves the source population sitting right where it is in the classical belt. It just changes how far the resulting dust ultimately travels. The second hypothesis digs into grain composition from a slightly different angle. A 2025 study modeling the effects of volatile rich versus purely rocky grain compositions on dust transport found that ice-rich grains behave measurably differently from rocky ones in how they respond to radiation forces. The interplay between sublimation, shrinking grain size, and radiation pressure produces a more extended dust distribution than purely rocky models predict. This is, in a sense, a refinement of the first hypothesis, and it can account for part of the excess, though probably not all of it. Particularly not the magnitude seen at the most distant measurements. The third hypothesis is the most consequential of the 3. It proposes that the parent body population itself extends well past 50 astronomical units, in numbers sufficient to sustain elevated dust production out there. If there are Kuiper Belt objects, even small ones sitting below the detection threshold of current telescopic surveys, orbiting at 60, 70, or 80 astronomical units, their mutual collisions and their ongoing bombardment by interstellar dust would generate exactly the kind of local dust population the student dust counter is recording as it passes through. This explanation doesn't require any exotic new dust physics at all. It just requires more material, more objects, more collisions, out in a region that was supposed to be largely empty. These 3 explanations aren't mutually exclusive, and all 3 effects might well be operating together, each contributing some share of the observed excess. But if the third explanation turns out to be correct, even partially, it fundamentally reshapes the architecture of the outer solar system. It implies the Kuiper Belt doesn't actually end where the object counts drop off. It implies the apparent edge near 50 astronomical units is an observational artifact, a limit of our telescopes rather than a limit of the belt itself, and that meaningful populations of icy bodies remain hidden in the darkness, too small and too distant for reflected light surveys to catch. yet numerous enough to sustain a measurable dust environment across tens of additional astronomical units. The collision environment of the belt adds another layer of supporting evidence. When New Horizons flew past Arrokoth, the near-total absence of impact craters on its surface carried a powerful message about the small body population in the cold classical belt. Impact craters accumulate over time as a surface gets struck by smaller impactors, and the number and size distribution of those craters tells scientists roughly how many impactors of various sizes exist in the surrounding environment, and how long the surface has actually been exposed to them. A heavily cratered surface implies a dense impactor population and long exposure. A lightly cratered surface implies either a sparse impactor population, a young surface that hasn't had time to accumulate many hits, or some process that erases craters as fast as they form. Arrokoth's surface is lightly cratered, and its age is independently known to be roughly 4.5 billion years, meaning it's been sitting in the cold classical belt essentially since the solar system formed, with no atmosphere and no detected geological activity to erase any craters that might land. That low crater count therefore points directly at the impactor population itself. There are far fewer small objects in the cold classical Kuiper Belt than models of collisional grinding would have predicted. This population appears meaningfully depleted relative to extrapolations from the inner solar system's asteroid belt. The cold classical belt hasn't been ground down by billions of years of mutual collisions into a fine powder of fragments. It has remained remarkably intact, its original size distribution largely preserved. That finding actually complicates the dust puzzle rather than resolving it. If collisions are less frequent in the classical belt than models assumed, then the dust production rate from mutual Kuiper Belt object impacts should logically be lower than predicted, not higher. Yet the student dust counter measures more dust, not less. That mismatch sharpens the underlying puzzle considerably. Either dust is being produced more efficiently per collision than current models account for, perhaps because icy surfaces fragment differently than rocky ones, or there are additional dust sources beyond the classical belt contributing to the signal. Interstellar dust bombardment across the belt's large surface area is one candidate, but models suggest it can account for the full excess on its own. The most economical remaining explanation is still the presence of unseen parent bodies farther out. The collision environment reveals something about the region's history as well. The cold classical belt's gentle, low inclination, low eccentricity orbits and its sparse small body population indicate this region was never subjected to the kind of violent dynamical upheaval that would have fragmented its inhabitants and pumped up their orbital speeds. Neptune's outward migration, according to the best current models, mostly affected the inner and resonant populations, largely leaving the cold classical belt undisturbed. Which means the cold classical belt is effectively a preserved sample of conditions in the outer solar nebula roughly 4.5 billion years ago. A region where material accreted into small bodies through gentle gravitational collapse, where collision speeds stayed low enough to build contact binaries instead of shattering them, and where the resulting objects have survived essentially unchanged all the way to the present. That preservation is genuinely extraordinary. In the inner solar system, the original planetesimal population was obliterated long ago. Asteroids have been shattered, reassembled, heated, melted, and reprocessed by billions of years of collisions and gravitational perturbations from Jupiter and the other giants. Terrestrial planet and moon surfaces have been continually reworked by volcanism, tectonics, erosion, and impact bombardment. Nearly every record of the solar system's earliest conditions has been overwritten in the inner system. In the cold classical Kuiper Belt, those records still exist, frozen into the shapes, compositions, and orbits of objects that have barely changed since they formed. Arrokoth isn't just a trans-Neptunian object. It's an artifact from the solar system's birth, preserved by extreme cold, vast distance, and a remarkably gentle dynamical environment. Accessing those records, though, is agonizingly difficult, and the obstacles aren't purely observational. They're logistical, institutional, and material as well. Even if a new mission to the Kuiper Belt were approved tomorrow, actually getting there would test the limits of current capability. The fuel problem alone is sobering. Radioisotope thermoelectric generators require plutonium-238, and the global supply of this isotope is extremely limited. The United States stopped producing it in the late 1980s and didn't restart domestic production until 2015, when Oak Ridge National Laboratory began manufacturing small quantities specifically for NASA. As of the mid-2020s, the production rate sits at roughly 1.5 kilograms per year. New Horizons alone used approximately 11 kilograms. A future Kuiper Belt orbiter, needing more power for a longer mission with heavier data demands, could require even more than that. The entire supply chain for the one material that makes outer solar system exploration possible is measured in grams per month. Then there's the problem of time. New Horizons reached Pluto in about 9.5 years, traveling at one of the fastest launch velocities ever achieved by a spacecraft. And it only managed a flyby, not an orbit. A mission designed to actually orbit a Kuiper Belt dwarf planet rather than simply race past it would need to carry enough additional fuel to decelerate into orbit after a decade-long cruise. That deceleration fuel adds mass, which demands a larger launch vehicle. Which increases cost and extends development timelines. Several mission concepts along these lines have been studied repeatedly over the years. None has ever been funded. The practical reality right now is that no space agency on Earth currently has a Kuiper Belt mission anywhere in its funded pipeline. New Horizons is the only spacecraft operating in this region, and there is no replacement currently being built. That means the window for direct, in situ exploration is finite. New Horizons' power output will keep declining. Its instruments will eventually degrade. Its trajectory is carrying it outward at roughly 14 kilometers per second, and within the coming decades, it will leave the Kuiper Belt behind entirely. When that happens, the only human-made instrument capable of directly measuring the dust, plasma, and particle environment of the outer solar system from inside that environment will simply be gone. Whatever questions remain unanswered at that point will stay unanswered until another spacecraft makes the same journey. A trip that would take at least a decade, even if it launched in the next few years, which, as things currently stand, it will not. Every single observation of a Kuiper Belt object, therefore, has to overcome the same cascading set of obstacles. Faint targets, near invisible motion, enormous distances, weak signals, limited spacecraft power, communication delays measured in hours. A finite fuel supply on the only spacecraft actually out there, and no funded successor waiting in the wings. The entire known population of over 5,000 trans-Neptunian objects represents more than 3 decades of painstaking work by survey teams, operating some of the largest telescopes on Earth. And only 2 of those objects, exactly 2, have ever been visited by a spacecraft. Everything else remains just a point of light, its brightness, color, and orbit measured with varying degrees of precision, its shape, its surface, its possible moons entirely unknown. We cannot know these things from this distance with current instruments. The physics of the outer solar system doesn't just make exploration difficult. It actively resists being known. And yet, every time an instrument has operated at the edge of its capability out here, it has come back with data that contradicted expectations. The dust was supposed to thin out. It didn't. The surfaces were supposed to be geologically dead. They weren't. The impactor population was supposed to follow the same size distribution as the asteroid belt. It didn't. The outer boundary of the belt was supposed to be sharp. The evidence increasingly suggests it isn't. The physics of the outer solar system tells a consistent story: the environment itself, the inverse square dimming of sunlight, the thermodynamic inevitability of cryogenic surface temperatures, the engineering consequences for spacecraft, the observational penalties for ground-based detection is well understood in its broad outlines. There's no exotic new physics required to explain why the outer solar system is dark and cold. The genuine mystery is what's actually populating it. And on that question, the data keeps outrunning the models. Beyond the classical belt, the scattered disk, and the resonant populations lie objects that don't fit neatly into any established category. And these outliers pose some of the most challenging open questions in the field. Sedna is the most famous example. Discovered in 2003, Sedna occupies an orbit unlike anything else known in the solar system. Its closest approach to the Sun is about 76 astronomical units, well beyond Neptune's meaningful gravitational reach. Its farthest point sits at roughly 937 astronomical units. A single orbit takes Sedna more than 11,000 years to complete. No known planet or dynamical mechanism in today's solar system can explain how Sedna ended up on that path. Neptune is far too distant to have scattered it there. The giant planet's gravity simply doesn't extend to Sedna's closest approach distance. Something else had to put Sedna on its current orbit, and identifying that something else has become one of the central open problems in outer solar system science. Several explanations have been proposed. A passing star, early in the solar system's history, could have gravitationally perturbed objects out of the outer Kuiper Belt and onto Sedna-like orbits, particularly if the Sun formed inside a dense stellar cluster where close encounters between young stars were common before the cluster eventually dispersed. Alternatively, a massive planet, larger than Earth but smaller than Neptune, could exist somewhere in the distant solar system on an orbit that has so far evaded every detection effort. Its gravity would perturb nearby objects, pumping up their closest approach distances and clustering their orbital orientations in a detectable pattern. That last idea is the Planet 9 hypothesis, and as of mid-2026, it remains one of the most vigorously debated proposals in planetary science. In 2016, Konstantin Batygin and Mike Brown published a paper in the Astronomical Journal arguing that the orbits of several extreme trans-Neptunian objects, those with closest approach distances beyond roughly 40 astronomical units and enormous overall orbits, stretching beyond 250 astronomical units, showed a statistically significant clustering in their orbital orientations. They proposed this clustering could be explained by the gravitational influence of an unseen planet, with a mass somewhere between 5 and 10 times Earth's, orbiting at an average distance of roughly 400 to 800 astronomical units. Such a planet would be extraordinarily faint, reflecting almost no sunlight at that distance. With an orbital period measured in tens of thousands of years, it could plausibly have evaded every survey conducted to date, not because it doesn't exist, but simply because it's too dim and too slow-moving to have been noticed yet. The hypothesis has picked up supporting arguments over the past decade. Objects influenced by a distant massive planet should exhibit specific, predictable dynamical patterns, and some objects matching those patterns have indeed turned up. Certain classes of trans-Neptunian objects with unusual tilts and closest approach distances emerge naturally from simulations that include a Planet 9 mass body. That's the hypothesis's real scientific strength, that it makes testable predictions. But it also faces serious challenges. In June of 2026, a team led by Yukun Wang at the National Astronomical Observatory of Japan announced the characterization of a Sedna-like object, and its orbit did not align with the clustering pattern the Planet 9 hypothesis predicts. Given that the original clustering signal depended on a fairly small sample of objects to begin with, each new discovery either strengthens or weakens the overall statistical case, and this particular addition weakened it. As Wang noted, The finding lowers the likelihood of the Planet 9 hypothesis and raises the alternative possibility that a planet once existed in the outer solar system but was later ejected entirely. None of this means the hypothesis is dead. The sample of relevant objects remains small, just a handful with well-determined orbits, and a single non-conforming orbit doesn't refute the idea any more than a single conforming orbit would confirm it. The statistical power of the test depends on total sample size, and that sample grows slowly because these objects are extraordinarily difficult to find. They're distant, faint, and nearly motionless from our vantage point. And every new discovery requires years of follow-up work just to confirm its orbit, the instrument most likely to finally resolve. This question is already running. The Vara-Rubin Observatory, perched atop Cerro Pachón in the Chilean Andes, officially began its legacy survey of space and time in July of 2026. Its enormous camera will photograph the entire visible southern sky every few nights for a decade, reaching depths no previous ground-based survey has managed. Within its first years of operation, the observatory is expected to multiply the known trans-Neptunian population by roughly a factor of 10. Among those discoveries will almost certainly be objects at the extreme outer margins of the solar system, on orbits current surveys have no realistic hope of detecting. If Planet 9 exists and has genuinely sculpted the orbits of distant small bodies into a detectable pattern, Rubin should find enough of those bodies to confirm or rule out the signal with real statistical confidence. Researchers have estimated somewhere between a 70 and 80% chance the observatory will directly detect such a planet within its first few years, if it's actually there. Bedijian has stated that this new wave of discoveries began arriving in the summer of 2026, and that it will provide a direct test of every current line of evidence for Planet 9. If the planet is found, it would rank among the most significant discoveries in solar system science since Neptune itself was identified back in 1846. If it isn't found, the orbital clustering will need a different explanation. A passing star, some kind of self-gravitating disk instability, or a mechanism nobody has proposed yet. Either outcome would meaningfully reshape our understanding of the outer solar system. But whether or not a ninth planet turns out to exist, the structural complexity of the region beyond Neptune is already firmly established. The scattered disk alone contains objects whose orbits range from near Neptune distance out to hundreds or even thousands of astronomical units. Objects that aren't sitting in stable orbits at all, but slowly evolving under the combined influence of Neptune, galactic tides, and the cumulative gravitational pull of the Milky Way's overall mass. Over billions of years, scattered disk objects can be nudged inward to become centaurs, or outward into the solar system's most distant reaches, potentially. The Oort cloud represents the final and most speculative layer of the solar system's architecture. No Oort cloud object has ever been directly observed sitting in place out there. Its existence is inferred entirely from the orbits of long-period comets, which arrive from seemingly random directions, with orbital periods stretching from thousands to millions of years. To reach the inner solar system from such enormous distances, these comets have to originate in a roughly spherical reservoir extending anywhere from about 2,000 to 100,000 astronomical units from the Sun, a shell containing what could be trillions of icy bodies, loosely bound by the Sun's gravity and slowly stirred by the tidal pull of the Milky Way and the occasional close passage of other stars. If the Oort cloud exists as currently modeled, it likely contains far more individual objects than the Kuiper Belt, by orders of magnitude, though its total mass may be comparable. Perhaps a few Earth masses of material spread across a volume of space, so enormous it approaches the distances between us and nearby stars. Proxima Centauri, the nearest star to our Sun, sits about 4.2 light-years away, equivalent to roughly 265,000 astronomical units. The outer edge of the hypothesized Oort cloud, at 100,000 astronomical units, would extend nearly 40% of the way to that nearest star. At those distances, the sun's gravity is barely perceptible, and objects out there are only loosely bound, vulnerable to being nudged inward toward the sun or flung outward into true interstellar space by the slightest passing disturbance dot between the known. Kuiper Belt in this hypothesized Oort cloud lies a vast, almost completely unmapped region, sometimes called the inner Oort cloud or the outermost fringe of the scattered disk. Sedna and objects like it likely inhabit this zone. Its population, its structure, and its relationship to both the Kuiper Belt and the Oort cloud remain essentially unknown, and the observational tools needed to properly survey it don't yet exist in any comprehensive form. It's a gap in the map so large that it genuinely dwarfs the portion we've actually charted. This is the honest state of the space beyond Neptune. It isn't a boundary. It's a transition from the organized, well-lit, gravitationally dominated realm of the giant planets into something fundamentally different. A region where sunlight becomes little more than a memory, where orbits are measured in centuries and millennia, where objects preserve chemistry from the solar system's first few million years, and where entire populations may extend outward in numbers. We haven't even begun to properly count. New Horizons drifts through exactly that transition zone right now. It woke from its most recent long hibernation on the 23rd of June, 2026, at a distance of roughly 64 astronomical units from the Sun, close to 5.9 billion miles from Earth. The signal confirming its health took 8 hours and 52 minutes to travel from the spacecraft to the deep space network station near Madrid, and from there onward to mission operations at the Johns Hopkins Applied Physics Laboratory. The spacecraft runs on updated autonomy software, designed specifically for the reduced power and extended communication delays of deep outer solar system operations. Its generator produces a little less power with every passing year. Its instruments continue to age. No second spacecraft is on its way to join it, and there is currently no funded mission to send another probe into the Kuiper Belt. And yet New Horizons is still collecting data. Its dust counter keeps recording impacts. Its plasma instruments keep monitoring the solar wind at distances where it's thinning toward the eventual boundary with true interstellar space. Its ultraviolet spectrograph keeps mapping hydrogen gas out in the heliosphere. During its most recent hibernation, the spacecraft quietly gathered and stored measurements that it's now transmitting back to Earth at rates measured in mere kilobits per second. Every fragment of information it sends has to cross a gap so wide that, from the spacecraft's own vantage point, the entire sun could be blotted out by something as small as the head of a pin held at arm's length. The mission team had hoped to identify one more Kuiper Belt object for New Horizons to fly past, extending the chain of close encounters that began with Pluto and continued with Arrokoth. Searches using the Subaru and Hubble telescopes haven't yet turned up a reachable target, and the spacecraft's remaining fuel and maneuvering capability limit exactly how far off its current path it could realistically travel. Unless a suitable target turns up soon, a possibility the Vera Rubin Observatory's deep survey may well help with. New Horizons will simply continue outward without another close encounter, eventually joining Voyager 1, Voyager 2, and the two Silent Pioneer probes as one of only a handful of human-made objects on a trajectory toward interstellar space. Even without another flyby, though, New Horizons remains genuinely invaluable, because it's the only instrument currently taking direct, in-place measurements of the Kuiper Belt environment. No ground-based telescope can measure dust densities at 64 astronomical units. No orbiting observatory can sample the solar wind out there. No Earth-based radar can probe the local particle environment from this distance. New Horizons is, quite literally, the only set of hands humanity currently has extended into that darkness. And what it feels out there, more dust than expected. A solar wind thinning toward its outer boundary. The faint glow of hydrogen in the outer heliosphere is information that exists absolutely nowhere else. Put together. The picture that emerges from the dust counter, the telescopic surveys, the spacecraft encounters, the James Webb spectroscopy, the dynamical models, the statistical debates, and the still unresolved hypotheses isn't a picture of an edge. It's a picture of a frontier. The solar system doesn't end at Neptune. It doesn't end at the classical Kuiper Belt's presumed boundary near 50 astronomical units. It doesn't end at Sedna's orbit, or at the outermost fringe of the scattered disk, or at the inner edge of the Oort cloud. There's no single, clean point where the sun's influence simply stops and interstellar space begins. The transition is gradual, spread across thousands of astronomical units, populated by objects that become progressively harder to detect and progressively less tightly bound to the sun's gravity the farther out you go. The familiar solar system, the one with 8 planets, an asteroid belt, and a bright, orderly stage of well-behaved orbits, is really just the well-lit opening chapter of a much longer, much larger story. It occupies a tiny sliver of the sun's total gravitational domain. Beyond Neptune, the story keeps going, but the pages get progressively dimmer. The objects out there are ancient, cold, dark, slow-moving, difficult to detect, and only partially mapped. Some are small and geologically inert. Some preserve volatile ices that, by all rights, should have been lost billions of years ago. Some display geological histories that their temperatures should have made impossible. Some likely belong to populations we've only just begun to infer from the faintest statistical hints buried in survey data. It's a bit like walking into an enormous library where you've only read the titles on the very first shelf and cracked open maybe 2 of the actual books. The remaining shelves stretch off into darkness, and nobody yet knows exactly how many there are. We can tell some of them hold material. We can detect the faint dust drifting between them. We have solid theoretical reasons to believe the full collection is enormous. But we haven't read it. We haven't cataloged it. We haven't even confirmed precisely how far the shelves actually extend. That, more than anything else, is what makes the space beyond Neptune so scientifically compelling. Not because it's hostile, though it is colder and darker than any environment humans have ever directly experienced. Not because it's dangerous, though every spacecraft operating out there functions at the absolute limits of its engineering. It's compelling because it remains genuinely unsettled. The picture is incomplete in ways that matter, and not just for understanding the outer solar system as some isolated curiosity, but for understanding the solar system as a whole. The Kuiper Belt structure encodes the history of planetary migration. The scattered disk's population constrains our models of how Neptune interacted with the primordial debris field that surrounded it. The presence or absence of a distant massive planet would reshape the dynamical architecture of the entire system. The Oort cloud's existence and properties determine where long-period comets, the ones that occasionally swing toward the inner planets, actually come from. The volatile chemistry found on distant dwarf planets informs our understanding of where water and organic molecules were available during the solar system's earliest history. These aren't obscure academic questions tucked away in some corner of astronomy. They're foundational questions about how our entire planetary system was built and how it continues to work. And the answers are sitting in a region so dark, so cold, and so remote that extracting them requires the most powerful telescopes we can build, the most patient survey programs we can fund, and the most distant spacecraft humanity has ever launched. Neptune was never really the edge. It was simply the last landmark we happened to recognize. Beyond it, the solar system doesn't end. It transforms. Orbits stretch longer. Objects grow fainter. Sunlight thins to a whisper. Temperatures settle to within a few tens of degrees of absolute zero. Distances stretch out until a simple message to Earth takes the better part of a day to arrive. And still, in all that thinning, freezing, darkening space, objects keep orbiting, dust keeps drifting, chemistry keeps operating, and surfaces keep evolving in ways we haven't finished mapping and may not finish mapping within our own lifetimes. The sun is still visible from 64 astronomical units. It remains a sharp, brilliant point, brighter than any star in the sky, still unmistakably the center of the system that bears its name. But it no longer warms anything out there. It no longer powers anything. It no longer dominates the sky with anything close to the authority it carries from Earth. From that far out, the sun becomes little more than a beacon marking the direction of home. And home itself sits nearly 5.9 billion miles behind. Ahead, there's only more darkness, more cold, and more unanswered questions. Receding outward into a frontier humanity has barely begun to explore. New Horizons drifts on, the only active witness we have out there, carrying instruments built by human hands into a silence so vast that even light needs hours to cross it. Behind the spacecraft, the sun keeps shrinking. Ahead of it, the Kuiper Belt continues, or ends, or quietly transforms into something else entirely. We genuinely don't know which yet. And that uncertainty, that unfinished map, that yawning gap between what we can currently see and what we strongly suspect is actually out there, might be the truest measure of just how much this part of the solar system still has to teach us. If you found this journey through the outer solar system as fascinating as we did putting it together, it genuinely helps to like the video and subscribe for more deep dives like this one, since it lets more people stumble onto stories about the parts of our universe that rarely make the headlines. There's a strange kind of comfort in realizing how much remains unmapped this close to home. We tend to picture exploration as something that happens light years away, among distant galaxies and exoplanets we'll never visit. But some of the biggest open questions in astronomy are sitting right here within our own solar system, in a region so close in cosmic terms that a single spacecraft launched in our own lifetime is still out there right now, quietly gathering the first direct evidence of what it's actually made of. What comes next depends almost entirely on patience and instrumentation. The Vera Rubin Observatory's ongoing survey will spend the next decade steadily filling in the gaps, discovering tens of thousands of new trans-Neptunian objects and testing, piece by piece, whether a hidden ninth planet is quietly shaping the orbits of the solar system's most distant residents. The James Webb Space Telescope will keep probing the chemistry of these frozen worlds, looking for more warm spots, more unexpected gases, more evidence of interiors that shouldn't be active but somehow are, and new horizons for as long as its aging generator keeps producing power. We'll continue sending back readings from a region no other instrument can currently reach, one faint, hard-won signal at a time. None of these efforts will fully close the gap anytime soon. The distances are too vast, the light too faint, and the objects too numerous and too well hidden for any single mission or survey to finish the job. But each new data point chips away a little more at the old, comfortable assumption that the solar system quietly fades into nothing past Neptune. It doesn't fade. It transforms into a colder, darker, far more populated place than the diagrams ever suggested. One that is still, after more than 4.5 billion years, actively shaping its own history in ways scientists are only beginning to understand. The last great world we recognize on the map isn't the edge of anything. It's simply where the light starts running out, and where the real work of understanding our own solar system has only just begun.